let's see why we do this. First, the modeling requirements may ask for this type of model. One example is Bayesian meta-analysis, in which you put together several studies. And the way how to put together these several studies is exactly via this hierarchical model. The second reason why you may want to use hierarchical model is the following. The priors may have the structural part and subjective part. And some part of the hierarchy can correspond to the structural part, the prior that you would like to have some particular structure or the domain, and then at the top of hierarchy, at the higher level of hierarchy, you put maybe non-informative or subjective priors. Another reason why you want to use hierarchy is the objectivity and robustness. Often you hear Bayesians saying, let the data talk about hyperparameters, meaning when you set the prior and the prior has the hyperparameters, parameters of its own, then a hierarchical model provides connection between data, between experiment and hyperparameters. And also, this may not be relevant now as it was about maybe 30 years ago. There are computing issues here, because sometimes the hidden mixtures or the hierarchies are easier to calculate and to implement than just the single prior, which is equivalent. So let's take a look at one example of the hierarchical model compared to the model that has single parameter data. And here, when you write the posterior is proportional to the product of the likelihood of yi's given theta and the prior on theta. The prior is common. There is single theta here. If you have thetas which are independent, then the likelihood is total likelihood of the model's likelihoods individual, f of yi given theta I times the prior for each theta I. Now, when you put the hierarchy and the hyperparameter phi on the top of these thetas and connect them with this hyperparameter phi, you get this hierarchical model. But thetas are not anymore independent. Thetas are exchangeable. So what is exchangeability? It is sort of, I would say, limited dependence in the following sense. The distribution of any vector of exchangeable variables, y1 up to yn, is equal to distribution of any of its permutations. So for example, when you think about joint distribution of this vector, if you permute these y's, the distribution does not change. That is exchangeability. Of course, if you have the random variables y's which are independent, they're automatically exchangeable because simply for independent random variables, joint distribution is a product and product is commutative. So any permutation of the indices or the random variables will preserve the distribution. However, the exchangeable variables may be dependent. One simple example is the following. If you take the multivariate normal, two-dimensional, with mean 0, and covariance matrix like this, so it is not identity, it has this rho, which is correlation between x and y. These two random variables are x and y. They are not independent. They are correlated, yet they are exchangeable because the distribution of yx is the same as distribution of xy.